star and delta connections. Star and delta connections. So however, the complete power system analysis we carry out assuming the power system is star connected. So one important point which you have to remember is that in power system analysis, we assume our system is star connected. Star connected. Okay. So what are the line to line voltage formulae and how we will do the analysis? We will discuss. For example, in a star connected system, if you suppose you take the loads are connected in this fashion. This is R phase, Y phase and B phase, or otherwise we use a nomenclature of A phase, B phase and C phase. Always you have to go the phase sequence in clockwise direction. Clockwise direction is the direction in which we have to proceed to find out the phase sequence. So this is the neutral point. Neutral. The voltage between any phase and neutral is called phase to neutral voltage. We will denote it with V phase. Similarly, the voltage between the two phases is called line to line voltage, which we will denote by VL. Understand? So the voltage between the phase to neutral is phase voltage. The voltage between the any two line to line conductor is a line to line voltage. Okay. Now the current through any phase in a star connected system, your phase current and line current are same. Phase current and line current are same. Understand? So in a star connected system, the line current is same as phase current. Line current is same as phase current. Both are same. Understand? Both are same in magnitude and phase. Same in magnitude and phase. Okay. Similarly, the line voltage is the magnitude of line to line voltage is root 3 times the phase to neutral voltage. Root 3 times the phase to neutral voltage in a star connected system. The line to line voltage magnitude wise, the line to line voltage is root 3 times the phase to neutral voltage. And the second point is the line voltage, the line to line voltage leads respective phase to neutral voltage by 30 degrees. The line voltage leads the phase voltage by 30 degrees in a star connected system. Okay, these 2 points we have to remember in a star connected system. Always remember the impedances that is connected between phase to neutral. This is called Z phase or ZL per phase, whatever. The impedance that is connected between the one line conductor and the neutral is the phase impedance. impedance, there is no concept of line to line impedance. There is no concept of line to line impedance. Always uh, the impedances are called per phase impedances only. Impedance are always treated as per phase impedance only. Okay. Second important thing is that suppose if you draw the phasor diagram, this is A phase voltage, which is which this is B phase voltage, this is C phase voltage. See why we are using the ABC, because it is an international uh, symbolic nomenclature which they use. In India we use RYB, ABC. It is equivalent in Indian system, it is RYB. Okay, because all the textbook and questions they follow this ABC notations only. We are going for ABC. So these are the A phase voltages, B phase voltage, and C phase voltages between the phase and neutral. Then what would be the, just give me 1 second. I'll try to block the noise. Yeah. Yeah. Can somebody unmute and tell whether you're able to see my screen and listen my voice?
Yes, sir.
Thank you, boss. Okay. Now, so you can imagine this is a phasor diagram for the loads. I mean, the system, star connected system. Always the sources are connected in star. I mean, the other end is always like this. I'm just for explaining, I'm telling. The sources are always star connected. So these sources are interconnected to the loads. The load part I have shown in the previous image. Okay. So these are the phase voltages. If you completely connect a resistive load, then your phase currents will be will be like this. That is, this is IA, this is IB, and this is IC. They will be in phase with their respective voltages. Okay. If you completely connect a resistive load. Okay. Now, if you connect a RL loads, then your phase currents will lag the respective phase voltages. This is IA, this would be IB, and this would be IC. By an angle, they will lag by an angle phi. Phi. Okay. So what is the positive direction of an angle? Anticlockwise. In phasor diagrams, the positive direction of angle is counterclockwise. Positive direction. What is the negative direction? Clockwise direction. Understand? Negative direction is clockwise. So when you're when current is lagging a voltage, you have to write it the lag in the towards the clockwise direction. Now here IA is lagging VA phase by an angle phi. Similarly, the IB is lagging VB by an angle phi, like that. Okay. The other situation would be if you have an RC load. If you have an RC load, then what would happen? It will lead the respective phase voltages by an angle phi. Now, I want to calculate the line to line voltage. The line to line voltage here is, suppose I want to calculate the voltage between A and B, VAB. So your VAB will become VA minus VB. VA minus VB. So if I first draw the minus VB will be 180 degrees opposite to the VB. This is minus VB. And if I add these two phasors, if I add these two phasors, because of by using parallelogram law, the equivalent would be like this. So this is your VAB. If it's not visible, I'll write it here. It is VAB. Now you can see this VAB leads. This VAB leads by an angle 30 degrees. It leads by an angle 30 degrees. And its magnitude also you can compute by using the parallelogram law. It would be root 3 times the magnitude of the phase voltages. Like that, the VBC, VCA will also be uh, will have same values and same phasor relationships. So what is the conclusion in a star connected system? The line current is same as the phase current, both magnitude and phase wise. The line voltage is root 3 times the phase voltage in magnitude, and the line voltage, line to line voltage, leads the respective phase voltage by 30 degrees. Okay, this thing you have to keep it in your mind. Understand? Now, what you have to remember in a delta connected system is that delta system. So again, the delta connected system is this is A phase, B phase, and C phase. Again, the clockwise. So now this is line current, whereas this is a phase current. This is a phase current, and this is a phase current. And whereas this is a line current. Okay. Here, the voltage between any two lines, the line to line voltage is same as the phase voltage. That means the phase voltage and the line voltage are same in delta connected system. The phase voltage and line voltage are same, whereas the line currents and phase currents are different. The line current and phase currents are different. So what you have to remember in a delta connected system, the line voltage is same as the phase voltage, both magnitude, both in magnitude and phase. This you might have learned in your circuits, but these are the things that we require. And similarly, your line current, magnitude of line current is root 3 times the magnitude of phase current, magnitude wise, and phase currents leads line current by 30 degrees. Here, phase current leads the respective line current by 30 degrees. This you have to remember in the delta connected system. Okay, here the line voltage is same as phase voltage, both in magnitude and phase angle, and the magnitude of line current is root 3 times that of phase current. And here, remember, phase current leads the respective line current by 30 degrees. Okay. So, and one more important relationship you have to remember is that Z delta, impedance in delta, this is Z delta, if you say. So in a delta connected system, impedance per phase is Z delta. Then the equivalent, if you transform it into a star, if you transform into a star, it will become 3 times Z star, 3 times Z star. Or you can write Z star is equals to Z delta divided by 3. Z delta divided by 3. Most of our system is balanced. We never get the unbalanced impedances. All the three phase impedances would be same. So in a balanced star to delta transformation, the relationships are the impedance in delta is 3 times the equivalent impedance in star connection. So it's the similarly the star connected impedance Z delta is Z star is equals to Z delta by 3. That is, I'll give an example here. Suppose this is the impedance. So it is a 4 at an angle 30 degrees is the impedance in every phase. So if you transform this into delta, then the equivalent delta impedances would be, they simply get scaled up by 3 times. What would be the impedance in every phase? 12 at an angle 30 degrees, 3 times. Understand? So similarly, if they give this delta, then the equivalent star would be every branch or every phase impedance will be 4 at an angle 30 degree ohms. Understand? Okay. Amma, is it clear, this portion? This is the source neutral. This is the load neutral. Okay. Let this neutral conductor be, let us draw it in green. Now, if you see, this voltage is VA A phase, VA, VB, VC. What are these voltages? These are phase to neutral voltages. Phase to neutral voltages. Then the current, let us assume that there is some impedance in every phase, some transmission impedance. This is ZA, ZB, and ZC. Okay. This is ZL, load impedance per phase. Now the currents in respective phases will be IA, IB, and IC. Okay. Now, if you apply the KCL at the load neutral, let this be the neutral current IN. By the Kirchhoff's current law at load neutral, what is the neutral current IN? The sum of entering currents must be equal to the sum of leaving currents. That is IA plus IB plus IC. What is the current that flows in the neutral? It is IA plus IB plus IC. Similarly, what is the current that is entering at this neutral, at the source neutral? That is again the same IN. IN is equals to entering current equal to IA plus IB plus IC. Okay. Either if you apply KCL at source neutral or node neutral, the relationship you're going to get is the same. Now, how does the currents circulate in every phase? The currents, hypothetically, they'll circulate. The A phase current will flow in this fashion. It is a closed path in itself. Similarly, the B phase will have its closed path and C phase will have its closed path. Now, if I try to compute what is my IA, my A phase current will become VA divided by, see how many impedances it will see in this loop. In this loop, it will see if the source is having some impedance, source impedance, transmission line impedance, plus the load impedance. Okay, this is ZA line, ZB line, and ZC line. So it is the combination of source impedance plus transmission impedance plus load impedance. Okay, S is the source impedance, TM is the transmission, or let us call this as line impedance, Z line, whereas ZL is the load impedance. Since it is a balanced system, so all the three source impedances would be same, all the three transmission line impedances would be same, all the three load impedances would be same. Understand? So this value would be IA. Okay. Similarly, your IB would be VB divided by ZS plus Z line plus ZL. Similarly, IC would be VC divided by ZS plus Z line plus ZL. Okay. Now, when do you say my three-phase system is balanced? Very, very, very important point. My three-phase electrical power system is balanced if my three currents flowing in the system are balanced. Three currents flowing in the system are balanced. Okay. So a three-phase power system is balanced if my three currents flowing in the system are balanced. First, you understand in a three-phase system, what do you mean by balance? Balance of voltages, balance of currents, balance of this one. If I take a phasor diagram of the three phase voltages, VA, VB, and VC. Okay, here the three phasors are balanced if their magnitudes are same. That is, first condition is there, mod VA is equals to mod VB is equals to mod VC. That means all three voltages or magnitudes are same, and they are separated in time space by 120 degrees. And they are separated in time by 120 degrees. That means how do we establish that their phase angle between each of these phasors is 120? See, if you do the phasor sum, it will be zero. It will be zero. Okay, how can you verify it? In time domain, if you write the three voltages in time domain, if I'm writing VA as Vm cos omega t, because it's A phase is a reference phase, R phase is a reference. Similarly, A phase is a reference, and VB would become, how would be VB? VB lags VA by 120 degrees. So it will become Vm cos of omega t minus 120 degrees. And similarly, VC will become Vm cos of omega t minus 240, because VC lags VA by 240 degrees, or equivalently we can write VC leads, the C phase voltage leads A phase voltage by 120 degrees. So I'll write plus 120 degrees. So if you add these three balanced voltages in time domain, just excuse me, ma, whenever we are writing time domain, we have to use the small letter symbols, that we should have to use this one VA, VB, VC. Okay. By default, they are all functions of time. Okay. If you add these three voltages instantaneously, that means at each and every instant of time, their sum would become zero. You can do carry out this exercise on your calculator by putting some random values for Vm and omega t. Let randomly you choose omega t value as some 20 degrees or 10 degrees. For whatever values of Vm and omega t, the instantaneous sum of these three voltages will become zero. Similarly, in phasor domain, how we establish the phasor sum of all three phasors would become zero. Okay, so for any in a three-phase system, for any phasor to be balanced, what are the phasors we are having? Phase voltage phasors, line voltage phasors, voltage drop phasors, and current phasors. So it this concept is applicable for all the phasors. So when do we say that the three phasors are balanced? When their magnitudes are same and when their phasor sum will become zero. When their phasor sum will become zero. So both these condition must be satisfied. That is, it is an AND gate between both the condition. AND gate. That means both conditions must satisfy. If one condition is satisfied, the other condition is not satisfied, then it is an unbalanced system. Both conditions must satisfy. So if these are the voltages in time domain, see, most of the impedances in power system, that means the sources, the lines, most of the impedance are inductive impedances only. Inductive impedances only. So, and even our load impedances are also inductive impedances. That means it's a combination of R and L, R and L. So in this case, my IA will become what? Vm cos omega t is my voltage in time domain. If I write the currents in time domain, IA of t will become Vm cos of omega t by, if you calculate the magnitude of all these impedances, it would be Zs square plus Z line square plus ZL square, that is the magnitude part, into, it will lag by an angle phi, because it is an inductive impedance all combined together. So IA of t will become Vm cos of omega t minus phi into square root of Z square plus ZL square plus ZL square. How I can equivalently write this one? I can write this as Im cos of omega t minus phi. Your IA of t will become this one. I'm writing all this magnitude part as Im cos of omega t minus phi. Okay. So your respective currents will be like this. IA, IB, and IC. Okay. So this would be the currents. Again, you can see the currents by themselves are balanced. Their magnitudes are same. That is, your mod IA, mod IB is equals to mod IC, and the phasor sum of IA plus IB plus IC equal to 0. Then my currents flowing in the system are balanced. Are balanced. Okay. So a balanced set of phasors are those phasors in electrical three-phase network which are having the same magnitude and which are separated in time space by 120 degrees, which can be mathematically established by taking the instantaneous sum of three phasors, it should become 0. Or if you do the phasor sum of the three phasors, it also will result in 0. Okay. So any doubt in this concept? We'll discuss more detailedly as we progress in this subject. So far, any doubt? Now coming back. So in a balanced system, I'm iterating the fact. What is it? balanced power system. A balanced power system is a power system in which all the three currents flowing in the system are balanced. That means that the three phase current magnitudes is same, and they are separated in time by 120 degrees. In a balanced system, what is a neutral current? That is, it is a phasor sum of IA plus IB plus IC. It is zero. It is zero. Understand? So, in a balanced power system, neutral does not carry any current. Neutral does not carry any current. Even the potential of the neutral point, any neutral point in a balanced three-phase system is zero. Even the voltage of neutral is 0 volt. Okay. Now the second important point is how to write the same value in phasor domain. VA is equals to some magnitude at an angle 0 degrees. So it will become VRMS at an angle minus 120 degrees. Sorry. I'm sorry. Yeah. This is minus 120 degrees. This is plus 120 degrees. So this will become VRMS 120 degrees. See, these are the phase to neutral RMS voltages, whereas VM is the peak value of phase to neutral voltage. What is VM and what is VRMS? So here VRMS is the phase to neutral RMS voltage. Here VM is the peak phase to neutral voltage. Okay. Now, what would be the currents? IA of t would be Im cos of omega t minus phi. Why? Because we are assuming our loads are RL loads. So how you write in phasor domain? IRMS at an angle minus phi. So your IB of t would become Im cos of omega t minus 120 degrees minus phi. So in phasor domain, you have to represent the same value as IRMS minus 120 minus phi. Similarly, IC of t is equals to Im cos of omega t plus 120 minus phi. This will become IC will become IRMS 120 minus phi. Okay. So if you carry out any of this one, that is VA of t plus VB of t plus VC of t, the instantaneous sum will be 0 because all three voltages are balanced. Similarly, IA of t plus IB of t plus IC of t is equals to 0 for all time t. This sum is called instantaneous sum of voltages or currents. Both will be 0 in a balanced system. Similarly, if you do the phasor sum, that is VA plus VB plus VC, just I'm drawing that upper line to denote it is a phasor sum, or IA plus IB plus IC is 0. The phasor sum of all three phasors would be 0 in a phasor domain. Okay. Then you can remember when phase voltages and currents are balanced, then respective line voltages and line currents are also balanced. It can be star connected system or delta connected system or whatever it is. See, first only thing, if the currents are balanced, everything else is balanced. So when the currents in the power system are balanced, it will automatically ensure that all the impedances in three phases are same, all the induced voltages are same, all voltage drops are same. So everything, even everything is balanced, then only the currents will retain their balanced system. If the currents are unbalanced, that means some elements are unbalanced in the system and the power system is unbalanced. That means here VAB plus VBC plus VCA, this condition is always valid irrespective of balanced or unbalanced. The sum of all line voltages is by default it is 0. And similarly the line currents IA, AB plus IC is 0. So this will be automatically taken care if the currents in the three-phase system are balanced. Balanced three-phase power system means the three phase or line current, the three line currents in the power system are balanced. Understand? If you look here, for the currents to be balanced, the induced voltages should be balanced. The impedances in per phase should be balanced. The load impedances should be balanced. Okay. So if there is any discrepancy in this, suppose everything is okay, but the transmission impedances are different, then again the currents will become unbalanced. So when the currents are balanced, automatically it ensures that all the voltages are in balanced condition, induced voltages are balanced, terminal voltages are balanced, voltage drops in the lines are balanced, and the three phase impedances, whether it may be source impedance, load impedance, or the line impedance, all of them are identical, all of them are same in all three phases. So current balance will ensure everything. Okay, this is about the three phase balanced power system. Okay, so what is the conclusion? Three phase power system is balanced if all the three currents, if all the three line currents are balanced, that is the current magnitudes are same and the phasor sum of three currents is 0. The current through the neutral conductor is 0 in a balanced three-phase system. The potential of all neutral points in the power system network is also 0. In a balanced system, the potential of any neutral point is equal to 0, which is same as the ground potential. Ground potential. Okay. Ground voltage or potential is 0. This is the reference that we take to measure all voltages. What is the reference? ground voltage. We always treat the potential of the earth as zero potential, and we take this voltage as the reference to measure all other voltages. So in a balanced system, what happens? Your neutral voltage will be equal to ground voltage. Okay, neutral voltage is equal to ground voltage. Understand? That is equals to 0 volt. Sir, which neutral voltage? All neutral. The neutral can be a generator neutral, load neutral, or a transformer neutral. All the neutral points in the power system will be at 0 volt when the power system is balanced. And we know ground potential is absolute zero. So when such a situation arises, if you connect some impedance between the neutral point and ground, let us call it as Zn or Zg, neutral grounding impedance. Zg is a neutral grounding impedance. This impedance may be connected at every point, at every neutral, or some neutral you may leave identical. So in a balanced power system, the voltage of neutral is 0 volt, the potential of ground is 0 volt. So there is no current flow either from ground to neutral or from neutral to ground, because both are equipotential points. Between two equipotential points, whatever impedance you connect, the current through that impedance would be zero. The current through that impedance would be zero. So one more important point is, in a balanced system, there is no current flowing between neutral and ground. In either direction, there is no current that is flowing between the neutral and ground, irrespective of whatever you have connected between them. Understand? Even if you short circuit them, there won't be any current flow because both are at zero potential. Okay. The potential of all neutral points in the power system network is zero. So all the impedances that are connected between the ground and neutral points can be ignored. Why? When the impedance does not carry any current, the voltage across it is zero. So any impedance across which the potential is zero, we can ignore it. We can treat it as a simple short circuit. No current will flow through them. We can completely ignore them. We can remove it. So all the impedances connected between the ground and neutral can be ignored, since the ground and neutral are at zero potential. Zero potential. So these are some important and salient points of a three-phase system which you have to remember. Okay. Am I any doubt here? See, one more important point which you have to do is that why we connect, or why we assume that our power system is star connected and we do analysis. Because the first point is, we assume our three-phase power system network is balanced. So in a balanced system, we know that the currents, voltages are balanced. That means their magnitude is same, but they are separated in time by 120 degrees. So rather than doing the analysis in all three phases, what we do the analysis in reference phase, that is A phase, and we use the same results for the B phase and C phase. So which will reduce the analysis part. Otherwise, doing three phase calculations in every time is lethargic process. So we assume our three phase system is balanced. With this, what advantages we can do? We can carry out the analysis between we can carry out the analysis between one phase and neutral, one phase and neutral. Okay, so neutral only exists in which system? Star connected system or delta connected system? Neutral only exists in star connected system. So that's why we always assume our power system network is star connected and we do our analysis. So analysis is carried out between reference phase. What is a reference phase? A phase, or in RYB nomenclature it is R phase, reference phase and neutral. Okay, and since it is a balanced system, all impedances connected between neutral and ground are ignored. Okay, so mostly the sources are connected in star. The transmission lines and loads, even though if they are connected in delta, we can easily transform them into equivalent stars, because since they are balanced impedances, we can just do the transformation with this transformation. Z star is equals to Z delta by 3, and we can easily bring them into star connected. And by connecting the power system in star connected, we'll have a neutral, so that we can do the analysis between phase and neutral. And the second thing is that we assume the power system network is balanced, so we can ignore the neutral, the impedance is connected between neutral and ground. Okay, so these are few things which you have to remember in our power system analysis. This is Z delta. Okay, so three-phase power system analysis is carried out assuming all the elements in the power system network are star connected. So wherever there are delta impedances, we'll compute their equivalent impedances and we'll replace them into star networks. Balanced three-phase power system analysis is carried out between reference phase. It can be R phase or A phase, and in neutral, the same results are equally applicable to other two phases. Okay, so these are few things which you have to know. Now, it is a it is instantaneous power supplied by a balanced three-phase source to a balanced three-phase load. Is the question is, what is the instantaneous power supplied by a three-phase balanced source to a three-phase balanced load? Very, very uh, many times an objective question, and you really have to understand this concept. So in a single phase, what is an instantaneous power? We have told you, in a single phase system, instantaneous power is the product of the instantaneous phase voltage multiplied by instantaneous phase current. P of t equal to VA of t into IA of t. Okay. Whereas in the three-phase system, there are three phases. You have to multiply with all three. VB of t into IB of t plus VC of t into IC of t. So the instantaneous power is given by the product of instantaneous voltage into instantaneous current of the respective phases. Suppose if it is a two-phase system, what is the instantaneous power? Instantaneous power will become, let us assume there are only two phases, VA and VB, then it would become VA of t into IA of t plus VB of t into IB of t. Okay, for a single phase system, what is the instantaneous power? Let us assume only A phase is there. It will become VA of t into IA of t. Understand? This is the formula for instantaneous power for single phase, two phase, and three phase. You can even extend it to any n phase system. Excuse me. So now he's asking for a three phase system. The instantaneous per PA of t is VA of t. What is VA of t? Vm cos omega t. Okay. And what is IA of t? Im cos of omega t minus phi. Since we are assuming RL load, because that's why current is lagging the voltage by an angle phi. If it is a resistive load, your product would be, what would be your product? There won't be any lag. It would be Vm Im cos omega t. If it is a capacitive load, it will be like this, plus phi. Okay. But whatever the instantaneous power term we calculate, it is applicable for all three conditions. It's resistive, RL loads, RC loads, pure inductor load, pure capacitor load also. Whatever the formula which we are deriving, it will be equally applicable. Okay. So let us take a uh, RL load because they are very common. This is a phase product. What about the B phase product? Vm cos of omega t minus phi into Im cos of, I'm sorry. Vb of t is Vm cos of omega t minus 120 into the current is Im cos of omega t minus 120 minus phi. This is a B phase product. What about the C phase product? Plus Vm cos of omega t plus 120 into Im cos of omega t plus 120 minus phi. I have not done anything. I have simply taken the respective voltages and respective currents VA, IA, VB, IB, VC, IC, and I'm just trying to multiply them. Okay. Now, if you take the product, I'm only concentrating on the first term. It is Vm, Im, this one. So I can write this directly as Vrms into IRMS into, that is one step I'm skipping, Amma. I'm skipping with step Vm Im by 2 into 2 by 2 into 2. So by 2 will become Vm by root 2 into Im by root 2. So the 2 term is there. That is 2 times cos omega t into cos omega t minus phi. Okay. Similarly, the second part I can write it as Vrms into IRMS into 2 times cos omega t minus 120 into cos omega t minus 120 minus phi. The third term will become plus Vrms into IRMS 2 times cos omega t plus 120 into cos omega t plus 120 minus phi. Okay. So now in every term, if I take Vrms, IRMS common, and I'm using one relationship which we have already discussed, 2 cos A cos B. 2 cos A cos B is equals to what? Cos of A plus B plus cos of A minus B. If I use this relationship, that is every term I'm writing it as 2 cos A cos B, which I am equivalently replacing as cos of A plus B plus cos of A minus B. Then what we're going to get? Arey, what happened? So I'm going to get cos 2 omega t minus phi plus cos phi. In the second term, if I do the same thing, I'm going to get plus cos 2 omega t minus 240 minus phi plus cos phi. The third term, I'm going to get cos 2 omega t plus 240 minus phi plus cos phi. Understand? So here, if you carry out the sum of these three terms, cos, let me take a brighter ink. Yeah, cos 2 omega t minus phi, cos 2 omega t minus 240 minus phi, cos 2 omega t plus 240 plus phi. Let us call this as x, y, and z. Okay, for any value of omega t and phi, the sum of these three will become 0. That is, your x plus y plus z will be 0 for any value of omega t and phi. You put randomly put any values, the sum would become 0. The sum would become 0. Then what is left out here? 1 cos phi, second one on. So cos phi plus cos phi plus cos phi is left over. So the equivalent result will be the instantaneous power term would become 3 times Vrms Irms cos phi. 3 times Vrms Irms cos phi. Understand? So the instantaneous power supplied by a three-phased balanced source to a three-phase balanced load is given by this formula, that is root 3 times Vrms Irms cos phi, where Vrms is the phase to neutral RMS voltage, Irms is the phase RMS phase current. Okay, and cos phi is the power factor between the cosine of the angle between the voltage and current. Okay.
Sir,
Yes, ma.
sir, here VRMS is RMS value of phase voltage, right?
Absolutely. Yes.
If line voltage is given, then we have to adjust.
Nothing you will have to know. What is the line voltage magnitude? Root 3 times the phase voltage. So if you replace with line voltage, one root 3 will be taken by that one. So it will become root 3 VL IL cos phi.
Okay, sir.
Because in star connected, line current magnitude and phase current magnitude is same.
Okay, sir.
Got it? Yeah.
Okay.
Okay. Yeah. So the one beauty here in this concept is that, let me take a couple of slides to explain. See, when we have computed the instantaneous power in a single phase system, what did you get? I hope you remember, or you can just go back and refer. My first term was Vrms Irms cos phi into 1 plus cos 2 omega t. Understand? There is one more term, that is Vrms Irms sin phi into sin 2 omega t. Understand? This is the instantaneous power in a single phase system. Again, there also, if you remember, we have done this exercise for A phase current and A phase voltage only. Okay. So this first term, we have coined it as an active term or a real term, real power term. And for the second term, we have coined this something called as reactive power component. Understand? Now, when we did the same exercise for three-phase system, the result which we have obtained is what? The result which we have obtained, the instantaneous power for three-phase system, it is just simply 3 VRMS IRMS cos phi. Is now, if you plot this against time, what is it? Is it a function of time? No, it is not a function of time. It is purely a constant value because your VRMS value is fixed, IRMS value is fixed, and once the load is fixed, then your the cos phi is also fixed, which is a constant value, which is not a fluctuating quantity like as in case of a single phase system. Okay, so that means if I draw the instantaneous power versus omega of t, this is mere straight line whose value is this one. Understand? So that's why three-phase system is so rugged, so stable. Understand? Because the instantaneous power that is being transmitted from source to load is constant. It is not fluctuating. That's why if you start a single phase motor, you require some support from a capacitor or from some other element because of this vibrating nature. If you start a fan, it will make some thud and it will start. Whereas when you start a three-phase big induction motor, it smoothly, it smoothly runs. It has longer life. It is more rugged. So that's why rather than going for two-phase system or four-phase system, people have settled down at a three-phase system because it's the most rugged and stable electrical system. You can see the instantaneous power is constant. It is not a function of time. Okay. The second important point is, which I want to tell you, sir, we had reactive power in single phase system. That reactive power is establishing a magnetic media in the end devices where we need to convert the electrical energy into some other form of energy. Here, the instantaneous power is not showing any uh, reactive power component. Does this mean? Does this mean that there is no reactive power in three-phase system? It's not like that. There is a reactive power flow in three-phase system, and reactive power flow is flowing in all three phases. That is A phase, B phase, and C phase. And C phase. But what happened here is that we have computed the reactive power for A phase. That is a reactive power component for A phase is this one. That is VRMS IRMS sin phi into sin omega t. Okay. If you similarly calculate the reactive power for B phase, you are going to get VRMS into IRMS into sin phi into sine of 2 omega t minus 240. If you only take the B phase terms and do the same exercise. Similarly, if you calculate for C phase, you are going to get again the same value into sine of 2 omega t plus 240. Understand? So this is the reactive component for A phase, B phase, and C phase respectively. If you add these three reactive components instantaneously, that means at each and every point of time, instant of time, if you add all three reactive powers, you can take sine theta plus sine theta minus 240 plus sine theta plus 240. The sum would become 0. That means instantaneously all three reactive power sums is becoming 0. Okay, that's why it is not being reflected in the instantaneous power formula. It is identical to your IA of just a minute, IA of t plus IB of t plus IC of t. What is this? The instantaneous sum of all three phase currents. What is this value? Its value is 0 for all time t. Okay, This does not mean that there is no current flow in the system. Currents are flowing in A phase, B phase, and C phase, but however, their instantaneous sum is becoming zero. Understand? Likewise, there is a reactive power flow in the network in all three phases, but however, the instantaneous sum of all three phase reactive powers is becoming zero. That's why this term is not showing the reactive component. Understand? Very, very important point. No textbooks will all teach these points. I hope you are able to get it. Okay. In a balanced three phase system, the instantaneous power transmitted from source to load is constant. What is the constant value? Root uh, 3 times VRMS IRMS cos phi. Okay. Now this question you can frame number of questions. You can see if I tell the question as if a three phase balanced source is feeding a three phase three phase three phase star connected resistive load, then what is the instantaneous power for resistive purely resistive loads? Your cos phi will become what? 1. So your answer would become 3 VRMS IRMS. That's it. That is the instantaneous power. For purely inductive loads, for purely inductive oblique capacitive loads, then your cos phi will become what? 0. Then what is the instantaneous power transmitted from source to load is 0. 0 is the instantaneous power supplied to a purely inductive and capacitive loads which are connected to a three-phase balanced source. This is also one question. Okay. For RL and RC loads, this value is same. But only thing is for RL loads cos power factor is lag and for RC loads it is lead. Understand? So the question can come in any form, but you should be understanding that a three-phase balanced source, three-phase balanced load, what is my instantaneous power? This is a term. So depending upon the values and the nature of load, this term can be interpreted in different ways. Okay. Now the second important point is reactive power component is missing in instantaneous power term. This is because the instantaneous sum of all three reactive powers in the system is 0. That is QA of t plus QB of t plus QC of t is equals to 0 for all time t. That's why that component is missing. So you have to know these things. Okay. Any doubt here so far? Whatever we have discussed. Next is complex power absorbed by three-phase balanced load. So what is the formula for complex power absorbed in single phase system? SS is Vs Is conjugate SR at the receiving end. SR is VR IR conjugate. Understand? So whereas in a three-phase system it will become the complex power supplied by three-phase source will become simply you have to multiply with 3. All the terms which I have told you, you have to remember for complete power system. SS means complex power at sending end or complex power supplied by the source. Similarly, SR means complex power absorbed by the load or complex power received at receiving end. Okay, it will become root 3 times VRIR conjugate. VRIR conjugate. Understand? So, if you take a balanced load here, I'm taking a star connected load. This is ZL. Always remember the impedances are per phase values only. There is no line to line impedance concept. All the impedances are phase to neutral impedances or per phase impedances. That is a better. In delta again you will say, sir, there is no neutral. How do we nomenclature? So you can say per phase impedance. Per phase impedance. Now let the line to line voltage is VL. The phase to neutral voltage is V phase. Understand? Now, what is the complex power absorbed by this load? Or complex power at receiving end, whatever may be. We interchangeably use these symbols. So the complex power absorbed by load will become how much? 3 times V phase, I phase conjugate. Whereas this is the phase current or line current. In star connected, both are same, flowing in the this one. Okay, right. Now what is I phase value? I phase is nothing but V phase divided by Z phase or ZL. Okay, V phase divided by Z phase. Okay, I've written the same thing. ZL. Okay, if I substitute in this one, what I'm going to get? SL or complex power absorbed by load is given by 3 into V phase conjugate into ZL conjugate. ZL conjugate. So this I can write it as 3 times V phase square. Why, sir? Complex number multiplied by its conjugate is square of that complex number divided by ZL conjugate. ZL conjugate. So all power system formulae we try to derive in terms of voltages, that to line RMS voltages. Now I can write this one as root 3 V phase whole square divided by ZL conjugate. So this will become VL square by ZL conjugate. So the complex power absorbed by the load is given by the line to line voltage across the load whole square divided by per phase load impedance. Impedance means per phase only. Load impedance conjugate. Load impedance conjugate. Okay. So we have derived, you should never ever forget this formula. Very, very, very important, which we'll be using many times in power system. Okay. Now, sir, we have assumed our loads are delta connected. We have assumed our loads are, sorry, star connected. Suppose if the load is given in delta, if the load is given in delta, what I have to do, sir? Very simply, you replace this is a star connected impedance, you just convert this delta into star. You're going to get what? For delta connected loads, you need not again remember the same formula. First, you can write down Z star is equals to Z delta by 3. So, which you can directly write. If you replace them, complex power absorbed by load will become VL square by Z delta by 3 conjugate. So which will give 3 times VL square by Z delta conjugate. Okay. Rather than remembering this formula, simply what I'll suggest is first convert that delta impedance into star impedance and apply the same old formula, this formula. If you are having more intuition to remember formulas, you can remember it becomes 3VL square by Z delta conjugate. Okay. So this is the complex power absorbed by any load across which we have to know what voltage and impedance per phase. Okay. So complex power absorbed by is given by the formula. The cell is equals to VL square by ZL conjugate. Understand? So complex power absorbed by a three-phase balanced resistive load. The same figure will be there. So here resistive load means your ZL will become RL. It's a purely resistive load. So your ZL becomes RL. So complex power absorbed by the load will become VL square by RL conjugate. Conjugate of real term is same. So your ZL will become this one, which implies your ZL conjugate will become same RL plus J0. Okay. So complex power absorbed by the load will be VL square by RL. VL square by RL, where RL is star connected impedance per phase. Understand? So what is the this about this one? The your SL is active power absorbed by load plus J into reactive power absorbed by the load. If you compare with this one, it will become VL square by RL plus J0, which implies load only absorbs real power whose value is given by VL square by RL, whereas the reactive power absorbed by the load is 0. Okay. So when your impedance is purely resistor, it only absorbs the real power. The reactive power absorbed by the load is 0. First important point. Second important point is the real power absorbed by the load does not contain any omega term or any frequency term. So the real power absorbed by the load is independent of frequency. The two important points are reactive power absorbed by the load is 0. Second important point is the real power absorbed by load is independent of frequency. Understand? The third and important point is the real power absorbed by the load is directly proportional to square of the voltage, load to load voltage. See, sending end voltage, line to line voltage, receiving end line to line voltage will be almost in the same range. Suppose if my voltage at the sending end is say 33 kV, 33.5 kV, let us for example, my receiving end line to line voltage will be roughly 33 kV. There is hardly a drop of 250 or 300 volts in the transmission line, but the difference will not be so drastic that suppose sending end voltage is 33 kV, the receiving end voltage cannot be 20 kV or 25 kV. The voltage drop won't be in such quantums. So more or less the sending end line to line voltage and receiving end line to line voltage will be more or less same with a 2 to 3% difference, 2 to 3% difference that in the voltage drop. So the real power absorbed by the load is directly proportional to the square of transmission voltage. I can say square of transmission voltage. That means if I go for higher and higher voltage transmission for the same load, for the same load connected at the receiving end, okay, I will be able to transfer more power to the load, more power to the load. Understand? So power transferred to the load is directly proportional to the square of transmission voltage. P load is directly proportional to Vt square. Square of transmission voltage. That's why we go for high voltage transmission. I mean, we'll discuss more detail later. So one of the advantages that if you go for higher and higher voltage transmission, you can transfer more and more real power or active power to the loads. Okay. Now, complex power absorbed by a three-phase inductive load. Inductive load. So in the previous case, all your loads were resistors. In this case, suppose your load is like that. All are inductors. So what the inductive impedance will be J omega L, J omega L, J omega L. Okay, this is a line VL, line to line voltage. Then the complex power transfer, what is the formula? VL square by ZL conjugate. Here ZL is what? 0 plus, because resistive portion is 0, J omega L, J omega L. ZL conjugate will become 0 minus J omega L. So if you substitute in this one, you're going to get SL, that is equals to PL plus JQL is equals to VL square by minus J omega L. So if I multiply with, if minus J, if you take to the top, you're going to get J into VL square by omega into L. So here, if you compare the real and imaginary parts, PL will be 0 and QL will be equal to VL square by VL square by omega L. So many var. Okay. This is the real power transmitted to pure inductive load. This is the reactive power. Okay. So again, since the loads are purely inductive in nature. There is no real power transferred to load, and the reactive power transferred is directly proportional to reactive power absorbed by load is positive. It is positive. That means reactive power absorbed by the load is positive. It is lagging reactive power. And second thing is reactive power absorbed is directly proportional to square of voltage and inversely proportional to frequency. Why? Omega is equals to 2 pi f. Understand? So with the with the decrease of frequency, the load absorbs more and more reactive power. It is sensitive to the reactive power absorbed by the load is sensitive to the frequency of the voltage or current. Understand? This is one important point. So let us try to solve this question based on that concept. Well, just read and understand the question. A shunt reactor of 100 MVA is operated at 98% of its rated voltage and 96% of its rated frequency. The reactive power absorbed by the bank is. So there is a shunt reactive bank. So this bank at rated voltage and frequency, how much reactive power it will absorb? 100 MVA. That is given. So at rated voltage and frequency, it absorbs 100 MVA. So how I can write this? Q absorbed by this bank, that is load, is 100 MVAR at rated voltage VL square by omega L. I'm writing omega as 2 pi FL. Okay. Now, what happened? 98% at 98% of rated voltage and 96% of rated frequency. How much will it absorb? It will become, your VL will be replaced by 0.98 VL square whole square divided by 2 pi L into 0.96 F. This will become how much? 0.98 square by 0.96 into the same value VL square by 2 pi FL. We already know what is the value of VL square by 2 pi FL, 100 MVAR. If you substitute that, you're going to get 0.98 square divided by 0.96 into 100 MVAR is the reactive power absorbed by the same bank when there is a fluctuation of voltage fluctuation is 98% of the rated voltage and frequency is 96% of the rated frequency. Compute this value and tell. Yeah, 100.04 is the right answer. I did not give it in the options. It is 100.04 MVA. So what is this reactive power? Lagging or leading reactive power? What type of reactive power is absorbed by inductor? Lagging reactive power. Lagging reactive power. Or the other name is positive reactive power. Okay. Yeah, similarly, if you take up the complex power absorbed by a pure capacitive load, so the this one would be minus J by omega C. I'm directly writing in the impedance form minus J by omega C. Now again the complex power absorbed formula is VL square by ZL conjugate. Here in this case our ZL is 0 minus J divided by omega C. Omega C. So ZL conjugate becomes 0 plus J by omega C. When you take conjugate, only the polarity of the imaginary term changes. So if you put in this one, SL is equals to VL square divided by ZL conjugate, that is J divided by omega C. It will become minus J into VL square omega C. So many value. So if you split it to SL, that is equals to real part plus imaginary part, you're going to get 0 minus J into VL square omega C, which implies the real power absorbed by load is 0. The reactive power QL is minus VL square omega C. So many var. Okay. Reactive power absorbed by the load is minus VL square omega C, so many var. This minus symbol will denote what? It is a leading reactive power. Minus symbol denotes leading reactive power. Okay. So rather than treating the capacitor as an element that absorbs the negative reactive power or leading reactive power, to reduce all our chaos and confusion, how we treat it as an element which supplies the positive reactive power or lagging reactive power. Okay, so for that I'll just explain. The reactive power supplied by the load will become what? It will become, the direction will change, it will become minus of minus VL square omega C. So it will become plus VL square omega C, so many var. So reactive power supplied by capacitor bank is VL square omega C, so many var. So Q supplied by capacitor load is directly proportional to square of voltage and frequency. So remember, in case of inductor bank or inductive load, the reactive power absorbed is directly proportional to VL square by frequency, whereas in case of capacitor, the reactive power supplied by capacitor is directly proportional to VL square into F. So in power system analysis, we treat capacitor as an element that supplies lagging, within bracket, positive reactive power than as a element that absorbs leading, within bracket, negative reactive power. Very, 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 very important point. So we treat all the capacitive devices as the elements that supplies the lagging reactive power rather than treating them as the elements that consumes the leading reactive power. Okay, so capacitor supplies plus Q, capacitors supplies plus Q, inductor, sorry, inductors consumes plus Q. So there is no confusion here. We always treat them as the capacitor as an element that supplies the plus Q, or lagging reactive power. Inductor as an element that absorbs the lagging reactive power. Okay. So I hope there is no confusion in this topic. Any doubts here, ma? Can I move to the next one? Yeah, try to do and tell the option which is the right option. Read this question and tell me. Out of the four, which is the correct answer? Read the question and tell me the answer. First option is wrong. Okay, first option you're telling option A.
Yes, sir.
No.
Sorry. C, sir. Sorry.
C is the right option. Okay, this is a way in which they ask some IAS questions. See, capacitor absorbs lagging reactive power, that is plus Q, and delivers minus Q, which is an opposite. It is completely opposite. So the statement is wrong. Similarly, when we come to the second one, inductor delivers minus Q, it absorbs plus Q, which is true. Third one is inductor delivers plus Q and absorbs minus Q, which is wrong. Fourth one, capacitor absorbs minus Q and delivers plus Q, which is true. So out of four statements, which statements are correct and which statements are wrong? 2 and 4 are correct, whereas 1 and 3 are incorrect statements. So the option would be C is the right option. Let us solve this problem and close this session. Read the question and understand it. Very good. 2200 watt is the right answer. So what he has given? He has given a two-phase system. Two-phase, three-wire system. Okay. So in two-phase, three-wire transmission system, the voltage between the A phase and neutral is given as, the voltage between A phase and neutral is 220 sine 100 pi t. And the voltage, the current flowing in the A phase is 10 sine 100 pi t. Similarly, the voltage between the B phase and neutral is how much? 220 cos 100 pi t. And the current flowing in the B phase conductor is 10 cos 100 pi t. Okay. So when you do the product, what is the, it is a, for a two-phase system, what is the instantaneous power formula? Here in this case, VAN into IAN, IA plus VBN into IB. If you do this, you're going to get 2200 sine square 100 pi t plus 2200 cos square 100 pi t. So which value is 2200 watt? That is the answer. Okay. Let us try to do this problem and close. Read the question again. Understand the question. Okay. Just read the question. I'll explain it. See here, a three-phase star-connected system, a three-phase star-connected load is being supplied by a three-phase star-connected source. Okay. Now it is a balancer system. What data is given? The line to line voltage is 208 volt, and the real power absorbed by the load is 432 watt at zero point 0.6 lead power factor. Zero point 0.6 lead power factor. Now he's asking calculate the impedance per phase. Calculate the impedance per phase. Okay. First you need to complex power absorbed is nothing but PL plus JQL. Okay. Now if someone asks you what is PL real power absorbed by this is given by SL cos phi. SL cos phi. Similarly, QL magnitude will become SL sin phi. SL sin phi. So here we know PL is equals to 432, which is equals to SL cos phi. So which implies your SL value will become what? 432 divided by cos phi, which in this case is zero point 0.6. So someone calculate and tell me this value 432 divided by 0.6. I hope it is 720, right?
720.
720 volt ampere. Now please remember the unit of real power is what? The unit of reactive power is VAR. The unit of complex power is VA. VA. Okay. I'll explain in the latter class that what is the difference between complex power and apparent power we'll discuss later. Now similarly, if I want QL, which is SL sin phi, what would be this value? 720 is my SL value. When cos phi is 0 0.6, what is sin phi value? Don't say 0.4. It is 0.8. 0.8. Okay. So this value would become how much? 72 into 8. 576 VAR. Okay. So my complete complex power will become, that is PL plus JQL is 432 minus J 576. Sir, why you have written minus? Because now my power factor of the load is what? Leading power factor. What type of reactive power will be absorbed by the load? Leading reactive power. So leading reactive power polarity is what? Negative. Be careful. So my power factor of the load is leading. That means it absorbs leading reactive power. It absorbs leading reactive power whose polarity is negative. Understand? So your QL is minus SL sin phi here because power factor is lead. Okay. So now what is the formula? We know that SL is equals to VL square by ZL conjugate, which sorry, which further implies ZL conjugate is equals to VL square by SL, which further implies ZL is equals to VL square by SL conjugate. Sir, why you are not taking conjugate for the numerator? Because numerator is a square term, which is a real term. So from this, we can calculate ZL as 208 whole square divided by conjugate of this one is 432 plus J 576. If you do this calculation, you're going to get the answer. You're going to get the answer. So what is the answer? 208 square divided by 432 plus J 576. 208 square divided by, simply do 720. What is the answer? What is the magnitude, ma? 208 square by 720? I hope it is 60.
60.
Okay. Yeah, 60. Then what would be the angle? Minus 53.1. Sir, how you can directly tell? Because out of all the four options, the impedance which is having a negative angle is this one. So when it is a capacitive load, the impedance will have a negative phase angle, right? So 60.53.1. Sir, how we would get 53.1? Here you are having this one. If you calculate the phase angle of this term, that is tan inverse 576 by 432, it will be greater than 1. So the angle will be higher than 45 degrees. So if you calculate tan inverse of 576 by 432, your angle will be 53.1. Since it is a capacitive load, the angle is negative. Understand? So if you are a very sharp student, you can easily eliminate two options. You can easily eliminate two options. Sorry, one option in this case. When it is a leading power factor load or a capacitive load, the impedance angle will be negative. Okay. Here, how see the options how he has given. All the negative angle values are same. 53.1 degree minus 53.1 minus 53.1 minus 53.1. So you only have to compute the magnitude part of the impedance. So in order to compute the magnitude of part of impedance, what is the best technique? You know the real power. You know the real power. So from this real power to calculate the only magnitude part, the simple it is VL square by magnitude of SL. Magnitude of SL. From this you are going to get the magnitude of the impedance. So once you know the magnitude of impedance, you can directly click the answer as 60.60 at an angle minus 53.1 degrees. Understand? I hope you have understood this question. Any doubts you can ask, or otherwise we'll close the session. We are having one more session today at 2 p.m. Okay. Any doubts you can ask, otherwise you can leave the session. Thank you.